Okay, let's get started. Hey guys, welcome to the second reading group session on large language models and transformers. Just a quick overview for those of you who didn't attend the first session. Every other week, Ashley and I are going to be presenting 2 papers in the field of large language models and transformers. For this session, we're going to be presenting one paper, which is a bit more foundational in the field of transformers, and then another one which presents an exciting application of large language models and transformers. So I'll be going first, and I'm going to be presenting a paper on vision transformers. Let me just share my screen. Cool. So yeah, I'm going to be starting off. Excuse me. I'm going to be starting off by presenting a paper titled "An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale." This was a paper published by researchers at Google in the conference ICLR 2021, and it introduces the model of vision transformers. So just a bit of background context. You guys know, 2017, we had the Attention is All You Need paper, which introduced transformers. And it basically revolutionized the field of natural language processing. And people have been trying to harness the power of transformers into different segments, not just natural language processing, but stuff like reinforcement learning, and in this case, image processing. So a bit more background into what existed prior to this. In 1989, Yale LeCun introduced the convolutional neural net, which had since then been like the state of the art for image processing. It involves using a shared set of filters, which would scan the image and extract important information from that, or like important features from that image, and use that then to make do classification, segmentation, etc. So you can see in this image of a dog, you have a square which represents your filter, and then the filter would scan the image, extracting important features like maybe the outline of the dog, different color mappings, etc. As for transformers, yeah, just a quick overview. I went over transformers in a previous workshop a couple of weeks back. You can see links to the recording of it and slides in our Discord channel. But just important information, it relies on the self-attention mechanism, which we're going to be covering a bit in the following slide. And when it was first introduced in 2017, it was used for sequential tasks and natural language processing. So yeah, in terms of the self-attention mechanism that we have for transformers, what it involves using or calculating the attention score between each pair of words in a sentence, or each pair of tokens in a sentence. That's for the natural language processing case. So take the sentence black dogs and red cats. For each word, for example, the word black, you'd calculate attention score corresponding to all the other words. So it would have a high attention score for the word dog, low attention score for any other word, because the word black is an adjective that describes the dogs. It doesn't describe cats, it doesn't relate it to anything else. And as you can see, you calculate that score between each pair. And this is considered an n-squared operation. So if we were to naively take this approach in order to analyze images, what you could do is you could calculate the attention scores corresponding to each pair of pixels. So for each pixel in the image, you'd calculate the corresponding attention score to all the other pixels in the image. And for images that let's say are n pixels by n pixels, this becomes an n squared operation, n to the power of 4. And for modern image standards, images that have millions of pixels, this is a very expensive operation. So what they introduced in the vision transformer paper is someone's mic on? Can we maybe just mute that? Because is distracting. Cool, thank you. But yeah, so what they introduced in the Vision Transformers paper is instead of calculating the attention score between each pair of pixels, you calculate the attention score between each patch, or like a patch of images, patch of pixels in the image. So you take an image like this, an image of a goose, and you'd split it into patches instead of just the pixels themselves, and you'd calculate the attention score between each patch. One sec, sorry, let me just take a sip of water. Okay, so we have an image, we split it into a set of patches. The patches, by the way, are usually like 14 by 14 pixels or 16 by 16 pixels. You take that 2D patch, for those of you who know, like it's actually 3D if you consider like the color channels that you have. You take that 2D patch and then you'd flatten it into a one-dimensional vector. And then this one-dimensional vector, you then like linearly encode it into an even smaller set of like vector inputs, a smaller dimension. And you do that for every patch in your image. And you take those encoded vectors and you pass them as input into your Vision transformer. Okay. So going a bit back to transformers, if you guys may recall, for those of you who know, since we process each word, and for like the natural language processing case, we process each word in parallel. And when you feed in just the raw word and like the sentence into the transformer, it doesn't know where that word actually lies in the sentence itself. It just gets a set of vectors. And so what you would need to do in the case of like sentences, you'd need to embed information about where that word is in the sentence. Is it at the start of the sentence? Is it at the end? Is it somewhere in the middle, after this word, that word, etc.? And for the case of Vision transformers, you practically do the same thing for the patches. Interesting thing that they did, instead of like noting the information that you embed into this patch vector, instead of actually just embedding like which row and which column it's in, you just number them like 1, 2, 3, 4, 5, 6, 7. Like you just number them one-dimensionally. And then that number is what you feed into your like positional, I guess, encoder. It spits out the vector, and then you add it to this vector that you get right here. And then another important detail about this positional embedding, for your regular transformers, the transformers that were first introduced in 2017, the process of positional embedding was just a fixed function that you specified, a fixed function that they had like written prior. For this case, it's actually like a learned function. It takes in the position of the patch in the image itself, and then it learns how to add, like how to extract information from that position that is useful when you later embed it into the encoded vector for each patch. So that's first implementation detail, positional embedding. Second implementation detail, you pass a vector corresponding to each patch of images or each patch of pixels of the image. And you also pass in another vector, which is called the like classification token. And for the case of transformers, each vector that you input, so each vector corresponding to like a patch here, you expect a vector as output. And for the case of like transformers, what that output corresponding to each of those patches would be is a vector that gives you information about how this patch relates to other patches in the image. So yeah, for example, in this like goose, the output of the transformer for this patch would strongly be related to like, I guess, the rest of the body of the goose, but it wouldn't be that related to like the water because this is like the head of the goose, etc. Now we pass in a vector for each of those patches, and then we also pass in this classification token. The interesting thing is this output corresponding to the classification token gets then fed into a classifier, which does our classification for us, tells us, oh, this is the image of a goose, etc. This might have been a lot. This image helps, like, I guess, summarize this overall structure for us. You take your image, you split it into patches. Each of those patches you pass into your transformer. You add like positional encoding to each one. And alongside each of those patches, you also pass in another classifier token. The output corresponding to this classifier token gets fed into a classifier. It's just a couple of linear layers, and that does the classification for us at the end. Tells us, oh, this is an image of a cat, a bird, ball, car, etc. Okay. Another couple of like implementation details that they went over in the paper. They actually do two types of training. They first train the model on a large data set that they have. They tested a couple of data sets, but the one that worked best was an in-house data set that they had. It consists of 300 million images. And then after that, they take the model that was trained on that data set and they fine-tune it using other smaller data sets. Now, an interesting detail is that when you're doing fine-tuning, this head that does the classification, you actually switch that out. You use a fresh one, and that fresh one gets trained during your fine-tuning. And another thing is the positional embedding slightly changes. Previously, we had done positional embedding based on just the linear ordering. So you do like 1, 2, 3, 4, 5, 6, 7, 8. When you're doing fine-tuning, you actually take into account like which row and which column each patch lies in. So this one is in like the first row, first column. This is first row, second column, first row, third column. You embed information about its like 2D position into the image. They found that that works best when you're doing your fine-tuning. Okay. In terms of results, so we have a couple of interesting results. Bear in mind, they compared this model on like, I guess, 2 benchmarks. They tested this model on a couple of like different test sets and for a couple of different tasks. And they compared it against the ResNet model. ResNet model is based on convolutional neural nets, and it's what's considered the current state of the art when it comes to like image classification and just image processing in general. And so they noticed that when you train both models, initially train them on a mid-sized data set, the ResNet, the model that's based on the convolutional neural net, actually performs way better than the model like the Vision Transformers model. But when you train both of them on a really large data set, something like their 300 million image data set that they have in-house, the Vision Transformer actually performs way better than your ResNet convolutional model. And the more you scale, like the data set that you pass in, and the more you scale the model, and the more time you give it to train, they notice that the Vision Transformer continues to be and like improve on its gap between it and the ResNet model. It becomes way better. So yeah, scales better. Now, talking about that issue with training our our Vision Transformer on a smaller data set, something like ImageNet, which is like even considered very large. Like ImageNet is, I'd say, mid to large size usually. But for the case of Vision Transformers, it's actually considered like a small data set. You need something in the order of like hundreds of millions. Why does it perform worse than a convolutional neural net based model? And that comes to an idea of inductive bias. Now, what are inductive biases? Inductive biases are like ways to analyze your image that are influenced by how the model is structured. So in the case of, let me go back to convolutional neural nets. For convolutional neural nets, you have just one filter or like a set of filters, but each filter itself goes over the entire image. So it's just one filter that extracts information from the entire image. And that gives it inductive bias. It allows the convolutional neural net to extract features, important features from the image, no matter where it lies in the image itself. This is actually a certain form of inductive bias known as translational equivariance. I know it's a lot of like buzzwordy words, I guess. It's a lot of complex words, but its meaning is actually very simple. CNNs, through their like structure, know that an image like this, an image like this, and an image like this, all of them which have geese at different positions in the image itself, they're all images of geese. However, something like the vision transformer doesn't know that. It thinks initially when you train it with a small data set, if you have a goose at the top left of the image, or if you have a goose at the bottom left of the image, or if you have a goose at the like middle right of the image, those may represent different meanings. Those may represent like different information, even though they're all just images of goose. And so it improves on its learning of that. It acquires that information, this like translational equivariance. When you train it with way larger data sets, it needs a lot more data in order to acquire that information. Whereas for convolutional neural nets, all this information comes embedded into the structure of the model itself. So yeah, in terms of advantages and disadvantages, for disadvantages, this means that you need to train your vision transformer on a lot more images in order to get results that are comparable with CNNs. But the advantage of that is that some of these inductive biases might actually be helpful. Other inductive biases might actually not be that helpful and might actually be a bottleneck to a machine learning model. So by not having any inductive biases, you kind of remove all the bottlenecks from the model itself. And through enough data, it in itself learns to analyze the image in an appropriate way, which actually becomes way better than like a CNN. And yeah, that brings us to the end of the Vision Transformers paper. Any questions, any concerns that you guys would like me to go over regarding the paper?
Thanks, Basil. Great job. I was actually just looking at the papers with code article, or not article, but their page just on vision transformers, and they had a graph of usage of different types of models over time, and it was interesting to actually, I can send it in the chat for anyone who's interested, but it's interesting because like ResNet since like 2017 was like the highest proportion of papers for ResNet focused, and then in 2020, like you saw vision transformers were proposed and they started to creep up, and now vision transformers represent the highest proportion of papers, and it kind of crossed over through about mid 2022. So definitely on the rise, I guess, in the image classification computer vision space. So
right, yeah, it is. And one thing that actually, I guess, is an advantage of using vision transformer. When the Google researchers were designing this vision transformer, they designed it in a way that it didn't really differ from your regular transformer implementation. And what that allows this model to have is that any like efficient implementations of your regular transformer model translated very well to vision transformers and made them a lot more effective, which made them very popular, as you had suggested.
Right. Yeah, interesting. And then also, I was just doing like a bit of reading before, and it looks like people are kind of combining like convolutional neural networks and vision transformers to get like a bit of the best of both worlds. Whereas you said convolutional neural networks have good inductive biases, but vision transformers lack. But then vision transformers have better like relational understanding of like within the image. So it's interesting how these two can be augmented to have like a better performing
very
model.
much so. Like in the paper itself, they actually test out a variant which combines both, like I guess the self-attention mechanism and convolutional neural net. They realized that, like in terms of overall performance, given enough like compute and given enough like training data, they both like the effect of convolutional neural nets isn't, I guess, is very much outweighed by the self-attention mechanism. But the current implementations that are coming out, which combine both, allows you to train a very effective model that combines both self-attention mechanism and convolutional neural nets with a lot more data. So there was this one, I think it's called DEIT by like Facebook, which produced comparative results to a vision transformer with like a lot less data used to train that model. So yeah, it's very interesting.
Very
Thank you for bringing that up.
Yeah, of course.
It's been really cool to hear about all of this. Thanks for presenting. I guess just a follow-up question you might have mentioned before, but like, are there concrete examples of problems that, like, if like I need to solve a kind of problem, is there a specific like thing that would tick off in my head for why I should use a vision transformer opposed to a convolutional neural network? I know in these like broad things we've discussed.
Right. So in terms of, I'd say in terms of applications, they both aim to like solve your image processing tasks. So I wouldn't say there's tasks that are more favorable for vision transformers over convolutional neural nets. It's just that currently, like with big companies, they're getting access to more and more data. They're getting access to more and more compute power. And the use of vision transformer just allows you to fully utilize all this data without really being bottlenecked by your model itself. So I'd say like convolutional neural nets would still be relevant in the cases where you have little data, little computational power, or like, I guess, time to like train your model. But in the cases where you do have a lot of data, in the cases where you do have a lot of compute power, you would aim to use a vision transformer.
Okay, cool. That ties in well with what you were saying, like because it scales so well.
Yeah. Very much so. Okay. Thank you guys very much for your time. If anyone has any questions, feel free to just message me after this on Discord. And yeah, for the second paper, Ashley, go ahead. Let me stop sharing my screen.
Sounds great. Yeah, actually, just give me 1 sec on my end. Sorry about that.
Yeah, no problem.
Okay, hopefully this is just somewhat relatable for you, but my computer is on its last legs and suddenly gave me a low battery warning, so I just didn't want it to drop off during our call, but just gonna start sharing my screen now. Sorry, I couldn't hear you for some reason. Can you hear me?
Oh, sorry, I was muted. Okay.
Okay.
If you want, I can share my screen instead.
No, that's totally great. I just wanted to plug my computer in so it didn't die halfway through. but here it should be all up and running in just 1 second. Perfect. So my paper, like we've discussed, is a lot more on the applications side of these things. So the idea is, can we go from scans of your brain to text and actually like read your thoughts, which is a really interesting problem. For this specific paper I'm talking about is the semantic reconstruction of continuous language from non-invasive brain recordings. And just for a little bit of context, I would show this video with the audio, but I think because my computer has just been having some tech issues, it's best if I actually just read off the subtitles to you, just so you guys know for sure what's going on. But it's part of this YouTube video that I'm just now sending in the chat if people do want to watch more of it, called The AI Dilemma, and they talk about some really interesting concerns having to do with the development of AI and society. So it's pretty interesting food for thought. But here they say, this is another example of translation. So here we took human beings, they stuck them into an fMRI machine and they showed them images, and they taught the AI, I want you to translate from the readings of the fMRI, so how the blood is moving around in your brain, to the image we can reconstruct. Then the AI only looks at what the brain does and doesn't get to see the actual image, and is asked to reconstruct the image of what it sees. So when you dream, your visual cortex sort of runs in reverse. So this means certainly in the next couple of years, we'll be able to start decoding dreams. Okay, so we can see what you're seeing, but can it reconstruct what you're thinking and your inner monologue? So here they did a similar idea where they had people watch videos and would try and reconstruct their inner monologue. So here's a video of this woman getting hit in the middle of her back and getting knocked forward. And then what would the AI reconstruct? I see a girl that looks just like me get hit in the back, and then she is knocked off. So this is the exact paper we're going to talk about that made this today. Hopefully that can just be a little bit of inspiration. And the earlier papers we see where it actually reconstructs the image are these ones. If you're interested in looking into it more, they use diffusion models. And on the top row, you can see the actual images that people were given to look at in testing, and then the reconstructed images below. And they're eerily similar in terms of like the actual meaning of what's going on in the image. On the right, similar thing, eerily similar, the reconstructed images, even if they're a lot less high quality. So existing methods for these brain-computer interfaces are something I'm just going to give a quick overview here. They can be really helpful to people who've lost the ability to speak. They can also be a tool for all of us humans to interact with technology in some futuristic world that using a phone is too much work for us. And then these decoders can reconstruct continuous language from brains, and this has been done already, but they need really invasive devices that are surgically implanted with electrodes, and often methods that are less invasive than that can only identify small set of stimuli, like general idea of letters, words, or phrases, and we can't like reconstruct someone's full inner monologue. So this paper attempts to reconstruct the semantic meaning of three things: perceived speech, which is when you kind of are hearing speech and what you're interpreting and understanding; imagined speech, which is when you imagine saying something, but you're not actually speaking, you're not actually using your tongue muscles; and then what you're thinking during silent videos, which is pretty self-explanatory. So the hope is that the same decoder can be used to decode brain images from all of this stuff under various circumstances and still work well. So we'll see if that actually pans out. The methods they used were training on fMRI data. So if you're wondering what this is, it's just a short form for functional magnetic resonance imaging, and it's used to monitor blood oxygen level dependent activity in the brain. So as the video mentioned, how the blood is moving around in your brain. And it's sort of a time series of an fMRI image. So some of you guys might have gone to the doctor, as this person is on the right, and gotten an fMRI image of what's going on in your body. But the functional magnetic resonance imaging method allows you to get multiple images and see the movement of blood within your brain. So one big pro of using fMRI technology is that it has great spatial resolution. It can really identify where in the brain movement is happening, but it has really bad temporal resolution. So you need about 10 seconds to do one of these scans, but humans speak at a rate of about 2 words per second. So that means that in one scan, you have to basically decode 20 words that person would have thought in their inner monologue, said out loud, heard, etc., etc. So this is called an inverse problem because there's many more words we need to decode than brain images to work with, which is why these sorts of problems aren't trying to decode the exact words, but more the general semantic meaning of like a phrase. So this is a diagram of the actual model they use to do this. Don't worry too much that there's a lot going on. I've tried to simplify it by just showing that this part A is the encoder. So that's when we actually encode the story that's being listened to, for example. And then the decoder is able to bring that general meaning of the story out into words and sentences we can actually sort of understand. One of the key things here is this has to be done for every single subject. So an encoder that encodes someone's thoughts is going to have to be different for each person in order to work effectively. That's at least the hypothesis. And the other key thing to note is that they're not predicting individual words. A language model sees the previous predicted sentence and kind of makes some candidate sentences to fill out afterwards. And all the decoder does is pick the most relevant from those to go forward with. And then that cycle just continues to repeat itself. So the main training set for this encoder decoder was 3 subjects that listened to 16 hours of stories. So they know the text going in, and then they look at their brain fMRIs and try and predict similar text coming out. So in terms of the experiments and results they have, so for this perceived speech, where they're having someone listen to something and they're trying to kind of guess what they're understanding from that and what they're hearing, they tested on different stories that were used in training data, which is a really good practice, as we all know. And then they were successful at a good amount of the semantic meaning. So there's a bunch of examples here. Maybe we'll just walk through the first one. Hopefully one of the general things you'll see though is the blue is exact matching of words, which is really cool. The purple is getting the general gist of what's going on, and the red orange is error. So this first one has quite a bit of error, and the actual stimulus was I got up from the air mattress and pressed my face against the glass of the bedroom window, expecting to see eyes staring back at me, but instead finding only darkness. And then the decoded sentence is I just continued to walk up the window and open the glass. I stood my toes and peered out and didn't see anything and looked up. Again, I saw nothing. So you can see that the air mattress part really wasn't picked up on at all. But in general, the gist was quite well picked up on, and I thought this was extremely impressive to see. Now, a more quantitative analysis of this, what they do is they use 3 metrics. The first 3, WER, BLEU, and Meteor, are just ways of comparing how many shared words 2 sequences have. So they look at the actual story and the predicted like outputs of what that person was hearing, and they match like how many of the words are similar between the 2. And those all perform better than chance. So they're predicting similar words more often than chance, which is really cool. And then when you look at the BERT score, which is actually looking at the shared semantic meaning amongst the sentences in the story and the kind of predicted story, it does a lot better than just chance. What you're seeing here on the y-axis is the standard deviations away. So something that is even like 7 standard deviations away, like the lowest one there, is still definitely doing a really good job, and something at 20 is performing very, very strongly. So this was really cool to see and very strong results. Before we dive into the next part, I'm going to give you my surface level understanding of what cortical networks are, because they'll be talked about. They're in the cerebral cortex, which is kind of the gray matter part of your brain we hear talked about a lot. That plays a really key role in memory, thinking, learning, reasoning, and everything like that. And they're connected regions of the brain with specific known functions. So the picture here is actually from the paper where they kind of show, for example, the ones in orange are known to have some sort of heightened activity when people are really thinking hard about language or actively using language. And you can see that they're somewhat clustered together in areas of the brain. So the next part of what they did was, for this sort of perceived speech, they wanted to see if they could decode across the different cortical networks. So here we have a bunch of examples where we have the actual part of a story that was listened to that says, I was like, no, I'm out of here. This is great. And I went and hid behind a cabana and he left. And then the decoded part from all these different specific parts of the brain that they're looking at. And you can see that for a lot of them, the key parts of the person left, it stands out throughout all of these ones here. So that's a really cool result. And one of the key results they want people to come away from this paper is that it seems like there's a lot of redundant information in these brain scans, and future brain-computer interfaces could attain good performance, but by just looking at a specific part of the brain. So that's really useful just in terms of having to like maybe wear less equipment on you, but also what they mentioned here for people that maybe don't have all of the parts of their brain intact. This is still a promising method to be able to allow them to communicate. So then imagine speech. This is when people are imagining they're doing something. So here, like they're saying something. So here they're telling stories. And they all told 5 1-minute stories twice. So they kind of got 2 recordings of each one of these stories. And then again, the results, they're not as strong, but they show that the decoder is able to guess the meaning of the story better than chance, which was really cool to see. The last thing we mentioned are silent films. So subjects watched 4 silent short films, and 1 fMRI recording was done for each. And again, the decoder predictions were significantly related to the film events. So here I'm not going to go over a quantitative look at it, but we're just going to look at an example here where you see 4 images at the top. And the decoded message is, she was very weak. I held her neck to get her breathing under control. And that's a really reasonable prediction of what would be going on in this short film here. So really exciting to see. In terms of limitations, they identified 2 key areas that the errors could be coming from. One is a bunch of random noise in the brain recording, and 2 is model misspecification, which I think largely just tries to capture that maybe not all the probability distributions they were interested in were actually in their training data. So they might need just a more diverse set of training data to expose them to more of those probability distributions. But they go and probe at some of these specific sources of error to see if they're a limiting factor. And when it comes to the training set size, what they did is they increased the number of scans they did for each of the subjects on each of the stories. And you can see that as you do more scans, the performance goes up, but it kind of starts to plateau at about 7 and doesn't get a lot better after that point. So from here, what we look at is the signal to noise ratio, which is what they're looking at on the right-hand side, seeing if that's a limiting factor. And what they do is they average the values over many different repeats of the test stories. And they see that this slightly improves performance because it does increase the amount of signal with respect to the noise. And all of this is very expected, but it also shows that these aren't maybe as big of limiting factors as you would originally suspect. One thing that I thought was I was surprised they didn't just see the effect of including more different stories, because I imagine that if you added more different stories to this and made them learn like 100 different stories and a lot more hours of listening, I think that would really improve performance. So I'm not sure why it wasn't tried. Now, in terms of hazards, there's one big one that we'll just be talking about here called mental privacy, because these sorts of decoders have the potential to really compromise it. And the definition of it is the idea that we have control over access to our neural data and the information about our mental processes and states that can be obtained by analyzing it. So the last part of this paper does a little analysis on this, which is really interesting to see, where they show that encoders need to be trained on specific subjects to have good performance. Otherwise, it's barely above chance. So like with their current model as is, they can't just go apply it to you, having never trained it on you, and be able to read your thoughts. So that's what this plot E shows, where the gray dots are the within subject level of performance, and you can just see they're a lot higher than the red or pink dots. And then plot F shows that decoding can be consciously resisted. And now I will tell you the strategies they said this can be done by, in case this stuff develops far quicker than we think and you need to know it. So they have count here, which means counting animals. That did not have significantly good performance. And if you do that while they're trying to read your thoughts, it'll help a little bit, but it won't help the most. What was the most effective they found on average was naming animals. So if you think of different animals to name, that can really throw these decoders off trying to guess your thoughts. And then almost just as good in terms of performance, and sometimes better, is telling a different story. But sometimes that's harder to do. So naming animals is a good, straightforward one. And then obviously none here is just passively listening. So you see that anytime you're just willingly listening and not actually trying to do something else with your thoughts, it's able to decipher them a lot better. And so will these decoders just get better in the future and these techniques probably not work? Yeah, but I guess we'll get to that later. So this brings us to the little discussion time section I had for my paper. Before we get there, and kind of part of the discussion, I just wanted to show this new hot off the press paper called Dream Diffusion that's very along similar lines to what I've previously showed you, where they're generating high quality images from brain EEG signals, but that's the key part. They're using EEG signals opposed to fMRI signals, and that's because these machines are more portable. They don't need to be operated by professionals. They're lower in cost, available commercially, and once again, not at all invasive, as in compared to actually implanting electrodes in your brain. So this is really some good food for thought on how quickly the stuff's progressing and how much more accessible it's getting. So the discussion points I had that I'd love to hear anyone's thoughts on are just, is it a good idea to develop this kind of technology? There's obviously a few people that this would really benefit, but it might be harmful. And if we do implement it, how can we protect our mental privacy? And then the third question is just, this is obviously mainly geared towards helping people who've lost the ability to speak, but it seems like a really powerful technology. And I wonder if there's maybe any other applications we can think of. I haven't quite fully put the puzzle pieces together, but I was thinking that there might be something on the communicating with animals side of things we could do using something like that.
Thank you guys so much for joining in, and we'll see you in 2 weeks' time.